third lecture on introduction to. All right, welcome to our third lecture on introduction to finite element methods. Thank you for joining this wonderful morning. I hope that the Lord has kept you. And today's lecture is just a continuation of what we have been doing in our past two lectures, but basically a continuation of the second lecture, kind of. And as we can see, sorry, I'm just monitoring to see why the video is not starting on my side. Good. It's okay. As I was saying that this is a continuation of what we were doing last week on the stiffness matrix and the finite element formulation for a spring element. So today we go ahead and look at what we call the bar element. And now, in essence, what we were calling the spring element in real life situations will not have springs, but we said it's a very useful instructive tool because it behaved in a way that we could be able to employ the basic fundamental equation, that is F is equals to K delta, in our equation without having so many variables, because it can only carry axial load. So today we are kind of handling the same trend, but now we go to a real finite element. And the finite element we are talking about here is a bar element. Now, this bar element, for your information, it can also be called as a truss element. And we are going to see why the two names. First, we note that a bar element or a truss element is an elastic bar that carries only axial forces. So, and what are the assumptions? Some of the assumptions that we have is that we assume a geometrically straight bar or an element. So what we are saying is that, so let's see, if I say the first assumption is that it's geometrically straight. So in essence, what we are saying at this stage is that whatever we are assuming is that the cross-section does not change. So it's not tapered, yeah? So don't mind my sketching. So we are talking of geometrically straight member. So we are supposed to be straight, right? So we are talking of just a straight. Oh, it's not working quite well. I should get a touch felt pen. I need stylus pen. Okay. So what we are saying is that if you look at it from 2D point of view, our bar is just like that. Okay. So we are not having cases where the cross section is varying. So that's the first assumption. The second assumption that we have is that the material obeys Hooke's law. Okay. So in essence, what we are saying, the equation of the fundamental equation for the finite element applies even on this case. So this material for the bar, it will obey Hooke's law, which of course we all know at F is equals to K times A. And in this case, I was saying, we may not be talking of K either as you know it, because now we know that E is used in other cases. So basically what we be talking of, mostly what we'll be referring here in deformation, we'll be talking of K delta, okay? So the material obeys Hooke's law. And you can see these two components, as I said, these are the constituents of the stiffness, because we say stiffness of a material, of a certain element encompasses two things. That is the geometry and the material characteristics. So those two assumptions, of course, now they are describing the stiffness. Now, the other assumption that we have or we make in this material is that the forces are applied only at the edge of the bar, all right? So but I know by now that you already now seeing why we call it the truss. So the forces, or we load, so forces only at the bar edge. you are going to see that this bar heads is what we're referring to as the nodes. When we have many elements, of course, when it's just one element, if you're just talking of a single element like this one, so we have that end and that being an head. But if we have now a continuation, of course, because in our assembly we have many elements, then we are saying these are the nodes. The head of one bar where they are connected to the other. That's what we refer to as the node. Now, just to a reminder is that I take my class attendance on the live chat, so that's why you should make sure you drop your name and registration number. Of essence so much for those people who have who use other names. But if you are using your name, like you have logged in your name, then you just need your registration number. But there are people who use maybe pet names and so on, so we need the name. All right. Now, the other assumption, the final assumption that this bar, or this, of course, this from the definition. The definition here, we had that this bar is subjected to axial forces only. So the assumption is that the bar supports axial loading only, right? That's a fourth assumption. Therefore, issues like bending, torsion, shear are not transmitted to the element via the nature of its connection. Why this assumption holds true is the nature of its connection. So now, let's now take you back to the simple structure that you've been using all the way wrong since you started structural analysis or finite, theory of structures. So you have been handling truss element so much, a truss structure. Don't confuse a structure and an element. So we discretize, we break down. So we are saying that's one node, another node, another node. And then this is an element by itself. This element one, this could be element two. We could be talking of this being node one, this being node two, this being node three, like that. So what we are saying is that, of course, for this truss, if you take this element, we said or been told that the truss only, the loads are applied at the nodes. We always assume that when we are doing the simple, of course, we are doing the simple analysis of trusses. Of course, in real life, you may find like the loads are not necessarily applied at the node. But to simplify the analysis for truss, we assume the loads are applied at the node. Number two, we assume that this member only carry axial load because the nature of the connection. What's the nature? Pin jointed. So these connections are pin jointed. So no rotation, no movement can develop. Okay. So basically, our member, the fourth objective, the fourth assumption that we are talking of, they carry on an axial load, bending, torsion, and other things like shear are not transmitted because the joint or the connection, the nature of connection is that it's pin jointed. Okay, too much of that. And that's why we are saying, you see the element we have been describing, basically we are talking of an element we have extracted from a truss structure. And that's why we are saying a bar element is also referred to as a truss element. The whole of this is the structure. Truss structure, whether it's 1, 2 member, of course, can we have 2 member truss? Of course, yeah, we can, if we are talking of a wall bracket. As simple as a 2-member truss, that is a member. But then when we take just one of its members, that's a truss. Of course, I'm differentiating between a truss structure and a truss member or element. Element, of course, those are the component of the overall truss. And this is why we are talking of, if you take just one of it, then we refer to it as a truss or a bar element. And you are going to see how we formulate the equation for this kind of an element. So we're saying there are a few things that we have mentioned. So we need to have some notation here, some definition. So this is the blue outline, of course. This is our truss element or a bar element. And then we said it carries axial load. So at the back of your mind, remember why we came with a spring element. Okay, the spring was like that. Then you say this is one node. Okay, node 1. Then you had another node 2. Then you talked of load application. Then you say this can only carry axial loading. Okay, compression or tension. So 1 degree of freedom. So same case with a bar element, it's a 1D truss element. Number 2 is that you have the node. Basically, we talk of general notation. You can say 1, 2, A, B, but we talk of the I, J, I being the lower, and then J being the higher node. And you see, even without yeah, I have shown the axis. We only need one axis to describe our degree of freedom. There is only a deformation in X direction. So that's why we can only have deformation. At this node, we can have either an elongation or a compression based on the nature of the force that is applied, whether it's tension or compressive force. So as you look at it, you see we can have deformation or displacement at node 1 or node I, UI, and displacement node J. Then F, the small letter, remember we talked of that. These are nodal forces, internal nodal forces or nodal members. Okay. Then now here, remember for our spring, the stiffness was just described using K. Okay. K being the elastic constant. Here, the rigidity or the stiffness of this member is now, because we are now dealing with a real structural member, we talk of the stiffness encompassing two things. One is the geometry, which in this case is described by the cross-sectional area, and two is the material characteristic, which is captured by the value E, Young's modulus. So when we come to the beams, you may wonder why now when we come to the beams, instead of talking just of A, we'll be talking of even I when we come to issues of bending. So when you come to the issues, that our member here just carries axial load, tension, compression. So what is of interest to us is the cross-sectional area, because we'll be talking of the stress in the member. No moments, no bending, okay? So we only need to know the cross-sectional area, or we are interested only in the cross-sectional area to be able to either design or analyze first and then design for our truss member. So you can see there is a kind of a relationship or a similarity between a truss member and the spring that we talked about. And just to jog your mind, we said the elemental stiffness matrix, of course, we said it's of this Hooke's law, F is equals to KE. This is the basic one that you started with, right? The basic one that you started with. And the K, of course, for the spring was the one we are talking of, KS. Now, the K, we described it as one K, or the KS minus KS minus KS, KS. I'm just putting the S's so that you know this is the actual stiffness of the spring. But the K out here, the capital K here, if you say you put in bracket, is a matrix, stiffness matrix. Okay, the KS for the spring is just the stiffness of the individual spring. But now we are talking of an element with two nodes, node 1 and node 2. We are talking of a two-node element. Okay, 1D two-node element. So that's why you see we talk of a stiffness matrix, which encompasses both behavior at node 1, UI, UJ. Okay. So don't confuse this K out there and the K's that we talk of inside the matrix. So in a similar manner, you can see if our spring, if our bar element behaves in a similar manner as a spring, then we expect still to have something of the sort. K minus K. If we can be able to express, we say the Hooke's law, if we can be able to express the bar element in this manner. So in this case now, let's give some few definition. So in this case, we have defined, of course, A is a cross-sectional area, E is the Young's modulus, of course, Fi and Fj, these are nodal forces, Ij are the nodes, Ui, Uj, those are the deformation, L is the total length of our member, X, of course, is the coordinate system, the direction of our axis. So this is what we are defining here. And we can go further ahead, and of course, we know strain. Strain can be represented with this epsilon. And then the sigma, this is the stress. And you can see from this point of view, we are saying U is equals to UX. What this tells you is that U, the deformation at any point, is a function of X. It's a function of where are we on our axis. Like the displacement at any point in between I and J depends with the length X. How far from the origin are we on this direction? And that any distance is expressed in terms of X, or you can use the notation X to designate or to define our location. Okay. If there's anything that you do not understand so far, you can just drop it in the chat section, then we can look at it together. So you should now be familiar, of course, from the many mathematics that you have handled, the SMAs. Then you'll be able to know when we put x, we are saying that this value is a function of x, or it varies with x. Okay. So that's the first step. Of course, we say that there are around 7 or 8 stages in the finite. Any finite element that you are going to formulate its equation, no matter how complex it can be, whether it's 3D, 2D, or 1D, basically the steps are similar. And the first one was, of course, you discretize, and then you select the element type. We are dealing with different elements. It's kind of the first stage. We have already assumed that we have done it because we are dealing with one element. So discretization or the breakdown, we have already extracted one element, and then we have said, let this be a bar element that we want to analyze. So the second stage, which we said this could not be performed using the spring element, was on the selection of the displacement function. What we do is this, or why we need this for your understanding is because of we said, let me take you back to our original, when we introduced finite element methods. I remember I was explaining using this circle, and I said if you want to get a circumference, let's say you want to get a circumference of this circle, basically you just need to use the formula. Circumference is equals to 2 pi r, okay, where r is the radius. Now, if went ahead and said, if let's say we didn't have this, okay, or because you may wonder when at what circumstances don't we have this analytical expression. Let's now assume that we have something that almost resembles a circle, but it's not regular. Okay. So we say there's no analytical formula that you can use to get a circumference of this or even the area. So basically what we do, we assume we can use some element, straight members, because we know the length of a straight member. We get the length of a straight member, okay? And then this length that we are talking of, this length, and now we can add them together because this is what we are talking of discretizing. And I want me just to go inside this circle and assume I'm approximating the circumference using some straight lines, okay? And then I enlarge them so that I get the point I want to make, okay? So as you can see, if we use straight lines here, assuming we didn't have an analytical formulation for determining the, of course, whatever, it's the area of the circumference that you want to determine. If we use the approximation using this finite element that we have introduced. So basically what we are saying, you see at the nodes, this is where now our finite element touches the axial curve. Of course, we know we have this. So this at the node is only where we have the actual solution. No, what we can call actual or exact. Okay. Number two, at the node, this is where we have the known. This is where we have the known values. So we have the known value here, we have the known value here. Whatever else in between, we can be able to approximate by interpolation. But to be able to know that to interpolate, we need to know how is the variation from this node to this node of whatever quantity that we want to determine. Let me now go back to our question at hand here. We are saying our element is, let's assume it's fixed here, and then we apply the root capital F here, external. So we expect some erogation, definitely, because the material obeys Hooke's law. Okay, we expect some erogation, whether it obeys Hooke's law or not. But because of it obeys Hooke's law, the erogation is directly proportional to the applied force. So there is a linear relationship, and that's why we said F is equals to K times the delta. Okay, and in this case, by the way, because we'll be talking of deformation in terms of U, because we see our notations here that we are using are U's. So let's at this stage now move directly to when we define deformation in terms of U. This should be K. This should be K, KU. Okay, KU. This is the format that we shall be now describing our Hooke's rule and the fundamental equation for finite element. Now, with this, K is equals to F is equals to KU. What we are saying is at any one point, right? At any one point along the length of this bar element, right? There is a linear variation. Displacement U, X, or U, which varies, which is a function of X, varies linearly. Okay? And that's why our assumptions are very important. Geometrically straight, material obeys Hooke's law. Okay? Because if material obeys Hooke's law and then maybe the geometry was varying, then maybe the deformation at different points or the elongation would maybe not be linear. But let's not get that there fast. So what we are saying is that the displacement U, which is equals to a function of X, is a linear function. Okay? Is a linear function. So in essence, what we are saying, you know, of course, the function, a linear function, you can just have it in terms of the equation of a straight line, where you can say U, you know, equation of a straight is Y is equals to MX plus C. So you can say U is equals to AX plus B. Okay. So this is what we are saying, select a displacement function. When we come to the beams, now in the beams, there shall be bedding. Okay. So looking at this, when we talk of the bedding, looking at the curvature of this, it's not far-fetched to assume our displacement, which will be our deformation here, our deflection. So our deflection, we can see it behaves in a quadratic manner. So we can assume a suitable displacement function, AX squared plus B, X plus C. So we assume or we select a displacement function. So we start for a bar element. We are saying is linear, it's behaving in a linear manner. So this UX displacement function, we can express it as an equation of a straight line. And I hope now you understand where we are getting these assumptions from. From the assumption that we define. And we know that it can either elongate, compress, no other form of deformation, no other degree of freedom. And then we are saying the material obeys Hooke's law, a linear edge. So basically, our function UX can be expressed as a linear function. And you can see this function now we are expressing them as a polynomial. Okay. Now, with that now in understanding, we are saying we assume the displacement varies linearly along the axis of the bar. So that's what I was explaining, why we assume linear. Why didn't we assume quadratic? Why didn't we assume cubic? Okay, because when you go to higher element, there are cases where now you have to assume higher polynomial, higher degree polynomial. So this is what I was saying, U, or the displacement, varies as linearly along the length. So basically we can express it as an equation of a straight line. So of course you don't stick with whatever we talk of Y is equals to MX plus, you customize. Y, which is U, X is equals to M. So you have two unknowns, A1 and A2. So you just need to determine or to evaluate A1 and A2 in terms of the displacement. So basically we borrowed from this equation of a straight line for those people who might be wondering. Y is equals to MX plus C. So we customized ours. UX is equals to A2X plus A1, or you can say A1X plus, no problem. So our stage is now to express A1 or A2 in terms of our unknowns. You know, you deal with what is given. Our notations or our quantities are displacement, length, and anything else that is given. So it's very simple. At X is equals to 0, so we want to know at this node, at the start point here, node 0. So you can definitely substitute. You can definitely see that one goes, and we are left with U or A1 is equals to U1. Because at X is equals to 0, UX is equals to UI. And the next thing you can also obtain when X is equals to L at this end, you substitute when X is equals to L, already you have obtained A1 is equals to U1. You want to obtain what is the quantity A2. And this is quite clearly explained, of course, in the note. We have, you express this constant in terms of node displacement. At x is equals to 0, we have obtained u1 is equals to a1. At x is equals to L, definitely you substitute that in this equation here. You're going to see u2 is equals to u1 plus a2L. Or basically we are saying a2 is this quantity. So in our expression, we are saying we can express ux is equals to a1, which is equals to u1, plus a2, which is equals to this quantity times x. This is what we have here. And then making, of course, we express our function in terms of u's. So you are saying 1 minus x of L, u1 plus x of L, u2. Quite simple. And this is what now we are calling our displacement function. And as you can look, see, it tells us, remember, we initially said, or we stated that u is a function of x. So it means it varies with x. And as you can see from the expressions here, you can be able to obtain the displacement at any point. So what we are saying is, in layman's language, or in simple terms, to explain to a layman, this is the erogated member, okay? This erogation that we get here is not just this member material here erogating at this node. So we are saying the erogation, total erogation that we measure, or when we say uj minus ui, is a summation of erogation experienced materials along this length, okay? So we are saying erogation at this part. When this member is erogated this way, if we had marked a point x here, which was maybe 2 or it was 3/4 L, yeah, it was 0.75 L. If that point is still, it can be seen here, and then we are measuring this length, we are talking of this length is not just the erogation of the material from here to here, but it's a contribution of all the material that is before this point x, okay? And again, now we are saying, at this stage, we are saying, using now this displacement function, we can be able to interpolate, because we say the known values are at u1 at u2. This will be the known values. So any other point here we can interpolate using this polynomial, which you call the interpolating function, the displacement function, okay? So you can confirm, when x is equals to 0 at this node, at the start point, node I, at node I, x is equals to 0. So this is there, this becomes 0. So 1 minus 0 is u1, then this one collapses. You can see ux is equals to u1. And you can check even for when x is equals to I. So you have our displacement function. It goes to step 3. You define the strain displacement and stress strain relation. Of course, this is, we should have an R here, strain. I hope you are able to follow from the very initial note, the lecture lesson number 1, where we explained, or we detailed, we listed the 8 stages of a finite element formulation. Okay. So this now is quite simple. Of course, you know how stress, strain, and displacement relate. Okay. We know how strain and relate. So strain, displacement, of course, you know strain is a change in erogation of the total length. But if we are talking of elemental strain of of a material here, very small at a point, a particle inside the member, then we talk of the derivative. And then the stress strain relationship, of course, stress is equals to Young's modulus times strain. Then the next stage is you want to derive the elemental stiffness matrix. So basically, if I take you back, this stage and the second stage, we could not be able to do with the spring element, because we said spring element is not suitable for stress analysis. Because the spring, we are not stress, you needed to get the cross-sectional area of the spring, but our spring is coiled, is helical. Okay, so basically, even if we apply the load, we are not applying at the cross-section of the spring of the wire itself, but we are applying over that configuration. You're saying it's not suitable for stress analysis. Okay, so these stages were not clear then, but we wanted to capture the general procedures that are followed in formulating the equations for finite element, for a 1D finite element. Now, at this stage now, we go to whatever we did in spring element, we do to the truss member. So we want to derive the stiffness matrix equation. You know, you derive in the step 4, step 3, you explain the strain displacement and the stress strain relationship. And these are given here. You can see them quite clearly. We had this and we had this in the previous step. So basically we are saying, we know strain is the same as strain, of course, is change in elongation of original length. So uj minus ui over L, which is the same as delta. And you can see this is capital delta over L, this total elongation. Again, from the strain, we know strain is equals to Young's modulus times stress is equals to Young's modulus times strain. But strain, we have been able to express it here. So that's what we are substituting in this part. Further, we know that, of course, stress is equals to force over area. So you can equate 5 and 6. Yeah, we are saying E delta over L is equals to F over A. Or in short, you can be able to express that F over A, F is equals to EA over L. If you get 5 and 6, it's equals to K delta. So you can see, if you look carefully here, this is basically what we had before. This is a Hooke's law with this part representing K. Because I had already explained to you that the stiffness encompasses both the geometry, and the geometry here is represented by the area and the length, and the material characteristic, which is now here represented by the Young's modulus. K, this is now the stiffness of the bar. Of course, this one we know from the strength of materials. I know in the strength of material, you've been talking of the bars, but the bars were now like that, downward, because the load now was being applied here. And you did all this derivation when there is a composite bar material and all that and so forth. You are calculating the behavior, mechanics of material. Okay, so K is the stiffness of the bar. So for the spring, K was Ks. So you can see F being K delta. Now you can go straight ahead because now it behaves in a Hooke's manner. It follows the Hooke's law. You can go straight ahead and start now formulating. Of course, F1 you express using the equilibrium procedure, condition of equilibrium to derive the elemental stiffness matrix. But I'll go straight ahead because you already did that in lecture number 2. You can revisit that. We just go straight ahead and say, for a spring element, we knew F is equals to K and then times the delta, and K here was Ks. So the formulation or the stiffness matrix for the element was K minus K. This is Ks minus Ks, Ks, okay, which we said could be written as Ks. Then we have 1 minus 1 minus 1, 1. Now we are saying the bar element behaves like a spring element with the stiffness being EA over L. So I can quickly go and say the stiffness matrix for the bar element. But remember, this one I'm only saying this because we already derived in lecture number. So you could go and revisit, see whether you can be able to derive from first principle using condition of course, using the Hooke's law and the condition of equilibrium to obtain the stiffness matrix. So K for the bar element, if I factor out our Ks here now, this is EA over L, 1 minus 1 minus 1, 1. And this is the stiffness matrix for a bar element. All right. Now, I can go straight ahead and then formulate the finite element equation. Once I have the stiffness matrix, whatever I just need to do is to introduce the F and K, because we know F is equals to K U. So I need to introduce the displacement vector and the force vector. And that one is done quite easily here. So this is the elemental stiffness matrix, whatever I was defining. And then if we introduce now the force vector, F1, F2, or Fi, Fj, and you introduce Ui, Uj, or U1, U2, then you have the elemental finite element equation for the bar element. So you can see the only difference from the spring element is that this stiffness for the spring was just K, the spring constant, but for us now for the bar element, the stiffness is expressed as EA over R. So you can go ahead and then do the assembly, you do the solution of the resulting algebraic equation, and you can be able to get the degrees of freedom. There are no degrees of freedom. Okay. So before we do that, because now we have stepped to a point that we already know, we are building this work, or we are building this lecture bit by bit. So I want to introduce a few things which we already have seen and we have already explained them, but I just want to lay emphasis on something we call a shape function. You see, we are saying, and I explained that for finite element, we said it's an approximation method. So exact values are only at the node. Anything else in between, we interpolate. Okay. And you see, we assume regards for a displacement function, the one that we have already derived for this bar element. We said we have the value of u1 will be known, u2 will be known. Any other value here can be interpolated. Okay. So sometimes we are saying this interpolating function that we assume the shape of the displacement field based on the type of element that we are dealing with, of course. And I slightly went ahead. I went ahead slightly when I talked of the beam member or the beam element. And I said, because the beam we anticipate to get the diffraction, you look at the curvature of that deformation, the diffraction. And then we said it wouldn't be far-fetched when we assume the displacement function as being maybe cubic or quadratic, something like that. Okay. Now, for this, we are saying this shape function, these are interpolating function that assume the shape of the displacement field. So look at this expression. This is the displacement field, the shape of the displacement field that we defined. But as you can see, ux, it's a function. Of course, we have u1, which is known at the node 1 and the node 2. And then there are these quantities which are varying. 1 minus x over L. This is varying as you move away from node 1. It's like this quantity is tied to node 1. This quantity is tied to node 2. So this quantity, we can refer to them, or we can just use a simplified symbol, just one symbol, n1, and then we call the second one n2, where n1 now is this 1 minus x of L, n2 is x of L. And as you can see here, if we try to sketch this, because you may be told to sketch something like this. So if you are to sketch first the shape of the displacement field, if you are to sketch the shape of the displacement field, this is the displacement, right? So the sketch in itself will be something like this, okay? We are saying U1, this is U1, and it varies linearly, and you know it's increasing if it's tension, okay? So this will be U2, this is U1. And of course, this is the variation, your equation, ux, which is equals to 1 minus x of L, and so on. So here is 0, here is the length L. Okay, u1 plus x of L, u2. So this is now the displacement field, a sketch of the displacement field. In a similar manner, you can have the sketch of these n1s and n2. So as you can see, n1 at x is equals to 0 at this start, x is equals to, when x is equals to 0 at u1, so you want to see how does it vary between 0 and the length L. So we are saying at this point, when x is equals to 0, n1 is equals to 1. So this value is 1. And we see n1, when x is equals to L, so L of L is 1, 1 minus 1 is 0. So n1 here is 0. Okay. So this is, of course, this is n1. This line represents n1. Okay, this is 1, is 0. Similarly, for n2, we want to see the variation from 0 at node 0 and L. And we are saying at the node 1, where we have x is equals to 0, of course, if x is equals to 0, If x is equals to 0, n2 is equals to 0. And if x is equals to L, n2 is equals to 1. You can see, no, this varies like that. So this is the n2. Okay, this is 1. So these are now the sketch of the these quantities, n1 and n2. And these quantities, you see this quantity n1 is tied to node 1. So it's like you move from node 1, it continues decreasing. By the time you get to node 2, it's like its effect is not felt anywhere. Same case with this. And these quantities are the ones we are referring to as the shape function. These are the interpolating function. These are the interpolating function that assume the shape of a displacement field within the element. So basically, it's all, we extract them, or we have extracted them from the displacement field, the one that we defined earlier. But now we have explicitly talked about them. You know, we could just have left them there because anyway, they are already captured in this expression. But now we are categorically and explicitly coming to sketch them, and you see how they vary. This shape function. They get interesting when we move to higher order element. You're going to see about the order of elements. But now when you talk of just linear, two-noded linear element, then they will be behaving in a linear manner like this. These are what we call the shape function, and that's a definition. And you may ask then, why do we need this, or what the purpose of this, or what we're talking about them here? So the thing, basically, most of the time, or at times, it's impossible. It's not always possible to obtain an exact solution. Of course, we say exact solution is where we have the empirical, the analytical expression that can be able to give us, like if you have a regular shape, circle, sphere, triangle, we have closed form solution. We have analytical formulation for that, and we can be able to obtain expression. But for the finite element where you say they are complicated geometry, then we will not be able at all time to obtain an exact solution. So what do? We assume a solution shape, or what we are calling distribution of displacement within the element, using an appropriate mathematical function. And these mathematical functions are in form of polynomials. You can revisit that in your notes, see what are the polynomials. So basically, like this, we assume this. So if you ask why do we need this shape function, why do we assume distribution of displacement function? Because if we assume, now the one we assume linear, and we know the exact solution is only at the node, using now this our assumption, we can be able to interpolate for any other value in between. But the value that we get in between is an approximation. Why? Look at this. Look at our simplified solution that we are talking about. And then look at, let's do what? The sketch that we are making. Okay. Okay. These are finite elements, assuming that this body, the outer body, the circle is irregular, so we don't have an analytical formulation. So what we are saying is that any other point, so this part, this node, at the node, it lies on the circumference here, so it's an exact value that you obtain. But any other value in between, like here, is an approximation of this value. So you see there is it's a difference, because we are talking of this length explaining or trying to give us this a curve. Okay. Anyway, what I'm saying is that the purpose of this interpolating function and the issue of the shape function is that because it's not always possible to obtain an exact solution at all times. Another thing I want to note is the issue of what we call the strain displacement matrix. Okay, so this strain displacement matrix, you recall, of course, definitely. I don't know whether I take you back there or we just write it down here. You recall that we explained that strain is equals to du over dx. Okay, I think it was the previous two slides. And then this was in step number 3. If you go back to step 3 of this formulation of finite element in this example that we are having, and then we expressed that our displacement function ux is equals to 1 minus x over L u1 plus x over L u2. Okay, so basically, if you now want to get the derivative of the first derivative of ux, so that you can get strain, you just need to differentiate this. So if you differentiate this with respect to x, you are going to get this here. You'll be left with -1 over L u1 plus this one you differentiate, you are going to get 1 over L u2. 1 over L u2. This is the same as du over dx, which is our strain. Okay, so we can write this in matrix form as -1 over L, 1 over L u1 u2. And in short, this quantity here, or we are saying strain, can be written as B, matrix B, times matrix U. And this one, sorry for this, this is a displacement vector. So you use the braces. So capital U. So where U represent this displacement vector, and the rectangular matrix B represent what we call the strain displacement matrix. Okay, this is what I wanted to mention. You may hear, or you may get them in some books expression, because now you find like strain will be defined in some books as stress. Sorry, will be defined in some books as Young's modulus times displacement matrix times the displacement vector. So you start wondering, even without showing this, so you start wondering what is happening here. So this is why I wanted to mention about the displacement strain displacement matrix. All right, so much with the theory. I believe we can go ahead and have an example. I'm looking at the chat area to see whether there is any question that is coming up. And from the look of things, I think people are satisfied. I don't know whether they are satisfied or they are confused, they are lost. So you can even chat there and say whether you are okay, whether you are understanding this thing. I know there's a rather simple concept, as I said, of all the theory of structure that you have heard, I believe this one can be considered to be the simplest, because it doesn't rely so much on what you have learned in other engineering things, apart from a few mathematics, algebra, and so on. Okay. So believing and hoping that we are together, let's look at an example here. It is a very simple example. We are given an assembly of 2 bar. So this fixed on this end, fixed on this end. At the mid, there is a load P that is applied. The lengths are the same, but as you can see, the cross-sectional area of this one is twice the second one. So the nodes are not given here, but we said the criteria for locating nodes: 1, where you have a change of geometry; 2, where you have point of load application; 3, at the support. Okay. So basically now, that with that in mind, we can go straight ahead and define our nodes. We say this is node 1, this is node 2, this is node 3, and then we have this as element 1, and this as element 2. Okay. What are you required to do? You are required to find stresses in the 2 bars. So you are required to find what is the stress. You see, in structural analysis, basically we stop at the point of load, when we get the reaction, when we get the moment, when we get the stresses, when we get that, so that when you come to design, now that is the input. The output of the structural analysis is the input in structural design. So whatever moment you get, whatever stress shear force you get, that's what now you use to calculate now the, like, what is the member sizes, what is the, if it's about the reinforcement, what the area of steel required, and so on and so forth. Okay, and that's why I always like a student to have a hard-on feel and experience with the structural analysis, so that they don't just jump in structural design. Because structural design, the garbage you bring in from structural analysis, it was not well carefully thought of. then it's just going to give you some result output, but some weird and crazy designs. Okay. So here we are going to find the stresses in the two bars. Basically, this tells you we are going to all the stage up to stress is equals to whatever force of area, Young's modulus times strain. Okay. So using the matrix method, before we get all these far here, then we need to do the stiffness matrix for each of the element. Remember, this one should now be at your fingertips, that for a truss member or for a truss element, K, so we have elemental stiffness matrix. So for a truss element, we have K is equals to EA over L. Okay. Then 1 minus 1 minus 1, 1. Right? So basically, for the first one, for the first K1, A is twice, is 2A. So you have 2 EA over L, then 1 minus 1 minus 1, 1. And basically K2 is just EA over L. Then the next one is you get the global stiffness matrix. So the global stiffness matrix is just the assembly. Remember, I told you you could use this to guide you. Note that the first one, K1, is U1, node 1, node 2. Then this one, K2 is node 2, node 3, node 2, node 3. But I said, when you put this in the stiffness matrix, these are not part of the equation. So if it's in a book you're writing, you could maybe use a pencil, faint. This is not part of the matrix. Don't make that confusion. So that now you can go ahead and see that the global stiffness matrix that you're going to have will be equal. We have the quantities of U1 corresponding to node U1, U2, U3. Then you can go ahead and take the quantity member here, you add with whatever is U1, you see what the total there, U1, U2, like so on and so forth. And you'll be able to obtain the overall global stiffness matrix. Okay. And this is it. The global stiffness matrix that we are looking for is this, up to this part. This is the K. But now at this stage, now we have gone ahead and introduced the force, the displacement vector, and we have also introduced the force vector, right? So that now we have introduced the displacement, you have force vector. So now we have K, we have the displacement, and we have the force vector. Remember, when you are writing by hand, you have to use this, because in the books they write in bold when they represent matrix, but for you, you can't write in bold, so you need to use these braces and appropriate symbols, because when we talk of a column vector, this should be bracing. When you talk of a rectangular vector, then this is not vector, rectangular matrix, then we use a square bracket. So you see already we had expressed, or we have defined our global finite element equation. Okay, so you can try using superposition method. You see that you can come up with this part for the K from the previous slide. That is by imposing or combining the elemental stiffness matrix for element 1 and element 2. Now, from here now, it's just a matter of solving. To solve this, we said we invoke the boundary condition. If you look at the boundary condition, this point is fixed, this point is fixed. So you have deformation or displacement at node 1, which is U1, this is 0. U2 is unknown, displacement at node 2 is unknown, displacement at node 3, of course, is equal to 0. So when you put this is equal to 0 and this is equal to 0, we know force 2 is given, is equal to P. Force 2, external force applied, is equal to P. So basically we said to be able to solve this quickly, you kind of, where we have the degree of freedom as known as 0, you remove the rows and the columns associated with that. Temporarily, not that we are throwing them away, so that you'll be able to solve this quickly. So you're only left with this element related with U2. That is 3 U2 is equal to this P. So if you go to the boundary condition, of course, I have invoked. So our equation 0, 0, F1, P, F3. So you go straight ahead. Our solution for this we are deleting first row and that row column, we obtain U2 is equals to P, or U2 is equals to PL over 3E. Okay. So you have already solved for U2 by removing the other rows and columns corresponding to known degrees of freedom as 0. So basically, we are saying U1 is equals to 0, U3 is equals to 0, U2 is equals to PL 3E. Okay. So you can go ahead and then get the reaction or the stresses. So the stress, we didn't need to get the reaction, no, but in this question, the reactions were not required, but you could go ahead and then start getting the reaction at the support. Huh? So stress in bar 1, because that's what is required. Huh? This is where I was explaining. Stress is equals to, stress 1 is equals to Young's modulus times strain 1, which is equals to E, B1, U1. And I remember we derived this part, the extra note that I have given you on that slide, you can revisit later. So you only need to substitute that E is equals to, okay, of course, these values, you just come and substitute them here. You find that sigma 1 is equals to P over 3A. Same case or similarly, for stress in 2, this one I have left is an field. You try to get the value of P2 by using the same. Of course, the equation is the same. Sigma 1 is equals to E epsilon 1, EB1, U1, and then substitution this. So the other one will be 2, B2, U2. Okay. And then here you'll be U2, U3. And it's as simple as it can be seen. So try to obtain the stress, the values here. Of course, I know in your notes you have them, but it's good to work out and see whether you can obtain it. And as you can see, stress in bar 1 is the same as stress in bar 2, but of course, different in nature. This is tension, of course. This one in compression. And even if you use what do you say? What with this approach? Even if you use the mechanical materials, strength of materials approach, you are still going. I know you know the stress for a bar element is equals to P over 3A. So this one tells you that this value that you have computed using the approximation method, which is the finite element method, is exact or is the same within the linear theory. And that's why some notes that we are giving is that bar 2, of course, is in compression. And we found that the stresses in element 1 and 2, they are exact within the linear theory. That is, even if we are using the analytical method in strength of materials and mechanics, you'll be able to get that the answers that you have obtained are the same, they are exact. So we know to get closer to the exact solution, in finite element method, what we do is by reducing, what we say, refining the mesh, reducing the size of the finite element. But if we have already obtained the exact solution, even if we like the value we could have obtained using analytical methods within the linear theory, then it doesn't help if we further divide the element 1 to infinite element. You don't need it. You don't need to define the mesh, this element to further finite element. These are just notes and interpreting the result. If you are given tapered bar, you need to get the average value of the cross-sectional area so that you can be able to obtain the elemental stiffness matrix. Okay. And then the other one is just a statement that if we need to find the displacement first in order to find stresses, since we are using displacement-based finite element method, direct stiffness method, displacement-based. That's why before we could get the stresses, we obtained the displacement first. Okay. And that's it. It's as simple as it can be. There's another example. A little bit, the cross-section are the same. The loadings geometry almost the same. But now we are leaving some gap here. There's a small gap here of about 1.2 millimeter. And then you are supposed to determine the reaction, support reaction at this part and this part. And as a hint, you need to decide to know that for us to have a reaction at node 3 at this support, it means we have to confirm whether the applied load here will make the erogation to exceed 1.2 so that there is a contact between this node 3 and this fixed support here. Otherwise, if there is no fixed type, then this would just be like a cantilever, but there's no reaction here. Okay. So think about it. These are some probable answers which I had calculated maybe some few years ago. You could try punching them in the calculator, see you get the same result. But the approach all the way up to the head of getting the reaction is the same way we have done to example 2.1. So the only trick that you are that's being introduced here is to determine this, but I have already given you a hint. Use what you know from your theory to determine the erogation for a bar element for this bar member, whether it will exceed 1.2, so that you can now say a contact will be established. Okay, try that, and then we see next time how is the solution. Okay, so far so good, and I don't want to go further than that for today, because if I go further than that, we'll be introducing a new concept, and I want you to digest steadily, gradually, so that by the time you are finishing this course, at least there's something that is left in your memory. So if you, for those people who have looked at the previous examples, this is what the other actually had. So make sure you be going through those examples. I mean, there's the tutorial question that I gave, exercise. So these are the answers. We had this string element system. So you can check to see whether you obtained something like this. Yeah, because we have to determine the stiffness matrix for the system. Number two, we gave this global finite element, this global stiffness matrix, and we wanted to see whether you can jog your mind by just looking at K1 is not a shared node. You move, you see K6 is not shared. Then you start, sketching the arrangement of the spring element. And this is the arrangement. So you can check again your answer, whether you had something close to this. One of the mistakes that you can do with this digital teaching is that if you just look at the examples, if you just look at them, they look very simple, right? But until a point when you start working them out by heart, that's when you realize where you get stuck. That's when you gain the confidence. Practice makes perfect. So don't just look at these examples, but dwell into them with your partner. You can check one another. You can do practice with one another. Go through those examples that we have already solved. Try to work them out without looking at the solution. Even if you know the solution is there, first work them out so that at least these concepts they get into your fingertips, right? All right. So next week we're going to move to another the same thing, but now we are going to see when the bar element is oriented in a 2D space. Okay, because when we talk of a truss, not all elements will be oriented in one direction. So we'll be having members in different directions. So you're going to see what happens then. So that's it from my end today. Now I'm welcoming some questions, both in the chat. I'm looking at it. I'm not seeing any question raised. And then I also want to share. I want to share the Zoom thing so that somebody who might be interested in asking a live question can ask. But again, I always say, it's if your question cannot be, you feel like you cannot be able to express it well. Otherwise, you don't have to join this link if you don't have any question. Okay. All right. I'm sharing it with the class lab right now. So in the meantime, if you have any query, either from previous class, you can ask it now. We try to address it. We have about we have quite some time. We can answer your questions. But you only have questions if you have been practicing. If you've not been practicing, then you not have questions because everything seems okay. Okay. So the class rep have shared the link, but only kindly log in there if you have a question you want to ask. If you don't have a question, no need. And by the way, there are no questions that I answer when we are off class. So if you have a question, you have to ask it very quickly when we are in class so that I can respond, other people can benefit. right? All right. I'm seeing the attendance. The class should be class rep. How many should you be? I thought you should be around 150. Last class and this class, I'm getting 130. Today, I don't know how many. And don't try to log in and then disappear. Eh? Because the good thing about this attendance is captures all through the different session who are logged in from the beginning to the end. It's different than the Kenneth one, where it just records anybody who came. Here I can sample at different times. All right. Okay, any question, anyone with a question? Everything is clear? Let me see from the chat. Is it okay? Everyone is okay? Mark Nyota, are you around? Are you okay? Victor Baluto, you are well? I'm waiting for some response so that I can know that people are well. Class rep, Pascal. All right, okay. Okay, good. Thank you, Victor. Okay, that's being the case. I know because you already have the note I've shared. I know you've been going through them. And as I'm saying, it is quite rather a simple thing. Seems like there's somebody. Yes, Anthony, any question? Brian, you have a question? I can see you have logged in. Aria Tracy. Leon Nyabura. Any question?
No question.
Then why are you here?
I prefer Zoom than YouTube.
No, Zoom. If most of you come here, it's be a lot of interference. I'm telling you. And also, this paid Zoom can only accommodate 100. It can only accommodate 100. The class is over. I was saying this so that if you have any question, anybody with a question, they can ask, and then we do it in class. But anyway, as you revise, as you visit your work, if there is any question that comes up, anyway, you can always ask it at a later date. All right. Thank you for your for attending. Thank you for concentrating. We end our class at that point. We meet next week. I hope you continue doing practice on the same. And more importantly, I hope that you people, you have installed the Abacus student version and you have started pre-practicing on it, because immediately you finalize this truss. Next week we finalize on the truss or the bar element. You should be able to attempt assignment number 1, the assignment. So by now you should have installed that for your practice. So thank you. We meet next week. If there's no question, it's bye-bye or from me.